To ensure the safety of their human coworkers, robots designed for human-robot collaboration in confined spaces, such as the one shown here, must be designed with a host of sensing modalities not typically present in traditional industrial robots. One of the most important of these sensing modalities is the ability to detect unintentional contact with the worker or the environment. Previous works on contact detection for Continuum robots have focused on small, lightweight robots, such as the one shown here. In these works, it was reasonable to assume the robot bent in circular, constant curvature arcs, and to ignore the effect of dynamics on the contact estimation. For the robot used in this work, however, the continuum segments are much larger in scale, and therefore these assumptions do not hold. To address these issues, in this paper, we adapt the generalized momentum observer, first introduced by DeLuca and Mattone, for variable curvature continuum robots in the space of modal coefficients that describe the local curvature of the backbone. This method uses the robot's dynamics to estimate the generalized forces due to external contact. We use these generalized forces to estimate the wrench applied to the robot using a constrained minimization framework that incorporates knowledge of the contact type. We then model the effects of dynamic state uncertainty on the uncertainty in the momentum observer. In the validation experiments, the continuum segment intentionally collides with a force-torque sensor, and the observer output is compared with the measured forces. We performed a total of 20 experiments with varying contact location, speed, and direction. Shown here are the results of the example experiment shown on the last slide. The graph on the left indicates the estimated forces in the local x and y directions, and the graph on the right indicates the generalized forces that were estimated during the experiment. The gray area, indicated here, represents a threshold past which the robot is considered to be in a collision state. This threshold was determined using the characterized uncertainty in the robot's dynamic state. In order to establish a performance baseline, we also compared the results of the generalized momentum observer to a direct estimation approach called the joint force torque deviation method. In the experiments, we saw that the generalized momentum observer performed better than the joint force torque deviation method in the local x direction and about the same in the y direction. Thank you for watching, and thank you to the National Science Foundation and Vanderbilt University for providing the funding for this project.